Howdy, welcome to another video discussion for Math 243 here at Portland Community College, Sylvania campus, Northeast Portland, Vernon neighborhood, remote station Utes. Today we're going to talk about, tonight? In the future when you hear this? Right now I'm going to talk about the binomial distribution and you'll hear about it now for you. Okay, the big idea here is there's a situation where we can have independent yes-no trials. Whenever a random event has only two possible outcomes, so-called success and so-called failure by statisticians, both so-called success and so-called failure have constant probability. That is, if the random event repeats, the chance of so-called success never changes. And since there's only two outcomes, well, the chance of so-called failure never changes. The cat's gone very cute. Well, and if the probability never changes from trial to trial, well, that means the trials are independent. So the third bullet there, independence for repeated trials, really is a reminder of the second bullet being true. These independent yes-no, I prefer yes and no to so-called success and so-called failure. Just think of asking a question. Does the cat belong on the table? He thinks he's a so-called success for being on the table. I just say, yes, he is on the table. Am I a so-called failure for allowing my cat up on the table? That's outside the scope of this course. In any case, independent yes-no trials, so-called success or so-called failure, they're called Bernoulli trials by statisticians and mathematicians, named for a couple of brothers whose last name was Bernoulli, who did a lot of fancy math work in Europe a couple hundred years ago. Classic example, flipping a coin, heads or tails. Same coin, flip it again and again and again. The probability of getting heads never changes. If it's a fair coin, it'll always be 1/2. And if that's what you consider a so-called success, well, the chance of a so-called failure, getting tails, will never change either, right? From flip to flip, the outcome of one coin toss doesn't affect the chances of heads or tails on the next flip, or the next flip, or the millionth flip, or the jillionth flip, or the gazillionth flip. The last couple numbers were little kid numbers and a number I saw on Facebook that's also not real. A non-example, something that's not a so-called Bernoulli trial, is anything where things are not independent. Like if you shuffle up a deck of cards, 52 playing cards, that's how I shuffle. Deal out some cards to play a game, a fun game, like maybe you want to play some hearts or spades. Those are good games. As you deal out the cards, if you're picking up your cards and seeing what you got, if the dealer's dealing and you're picking up your hand of cards, every time you see one of your cards, that changes your knowledge of what other cards are still available, what the chances are and the probabilities are of being dealt remaining cards. They change every time a card is dealt. That's dependence and changing probabilities, not so-called Bernoulli trials. The last example here is one from real life that's not quite actually a Bernoulli trial because, well, if you're not familiar, Damian Lillard is a really talented basketball player. He plays basketball professionally for the Portland Trailblazers of the National Basketball Association. He's also a pretty cool guy, a seemingly loving family guy with some nice, really cute little kids. A talented musician. He's actually a good rapper. And he's gone out of his way to promote and help other young and upcoming rappers connect with audiences. He's pretty cool. And one thing he's really good at is making a free throw. If you're not a basketball fan, that's when a basketball player takes the basketball, it's like this big. They stand at a line 12 feet away horizontally from a basketball hoop that's 10 feet up in the air. Big old hoop with a net on it. They throw the basket up, see if it goes in. That's a free throw if you're not a basketball follower. If you are a basketball follower, that was probably an unnecessary description. In any case, it's hard to make a free throw for people who don't practice. I can't really make them unless I get lucky. But Lillard has practiced his whole life. And at the time I made this slide, his chance of making a free throw empirically, based on his past performance in the National Basketball Association, was 88%. It's actually slightly better than that today. Okay, but you know, shot to shot, when he steps up to take a shot, he has about an 88% chance of success when I made this slide, empirically. Okay, so you can use this Bernoulli trial idea to apply it to real life stuff as well. And since I love the Portland Trail Blazers, and I love, you know, as you love your favorite athletes, Damian Lillard's work as a trailblazer and the impression he makes as a cool guy in the community. Like when he was on the front line in the Black Lives Matter marches, whether he participated in front line. Good guy. All right. So here's our example. This is going to be our example of how this binomial distribution works. And it's kind of complicated. Make your free throws. Let capital K, and that's the letter that our book likes for random variables that are officially known as binomial distributions. So it's a random variable, recall, is some numerical outcomes and their corresponding probabilities. When you can list out the outcomes, it's called a discrete random variable. And that's how this is going to work. Capital K is the random variable with outcome K is the number of free throws Lillard makes out of n equals 3 attempts. So he steps up to take 3 free throws. Any of them could be made or missed. Our job is first to find the probability model for K, the number of free throws Lillard makes out of 3 attempts. We got to list all the outcomes out and calculate all the probabilities. You'll probably remember from your work with discrete random variables in the previous chapter that the probability calculations are pretty complicated, and that's going to be true here as well. Since there's 3 free throws being taken, we're going to make a pretty big tree diagram to show how everything can go and calculate all the probabilities. Let's go over into our notes document, Jamboard, and do that there. So here we are. It's going to be binomial. I'll just call it make your free throws. Just like the slide. Oh my, that's some terrible typing. We'll see how we do. Okay, now remember, anytime we have a random variable, it's got a capital letter for a name, and you just want to say what it means. Number of made free throws out of 3 attempts. And so when we make a probability model, we want to list out all the outcomes. Since capital K is the name of the random variable, the individual outcomes are going to be called lowercase k. Like many of our examples of discrete random variables in previous work this quarter, they're not that hard to list out. If anyone steps up to take 3 free throws, there's 3 ways it could go. Make 0 free throws, like if I tried right now. Make 1 free throw, make 2 free throws, or make 3 free throws. It's just straightforward. The challenge is figuring out the corresponding probabilities, that lowercase p for each one. This is actually a complicated task that we're going to work through slowly, one step at a time. Now, before we start working on this slowly, one step at a time, I just want to let you know you won't have to be able to do all this slow, one step at a time stuff yourself for your work. I'll be showing you how to get these calculations done very quickly and accurately using your buddy, technology. The reason we want to look at the calculations in detail is the same reason that even if you're not going to be an automotive mechanic, you kind of want to look under the hood of your car with a mechanic every now and then if they're working on it, so they can explain what's going on and you can kind of understand a little bit better what's going on under the hood. So the next few minutes, what I do on these slides to calculate probability, it's really looking under the hood of the car that we call the binomial distribution. Too many air quotes around different things. Gotta stop. Too many. Okay, so to make this 3 shots, make miss, yes or no, make it yes or no, the second shot, and make it yes or no, the third shot, that's going to give us a tree. Now, I'm actually going to pause the video to draw the branches of the tree because it just takes a couple of minutes. I mean, pause the recording. While I paused the recording, I typed up a bunch of Y's and N's for yes and no, a shot was made or not, here to make my tree diagram, and I drew the first 2 branchings that show that yes or no, Lillard could make the first free throw. If yes, he made the first one, he could yes or no make the second one. If no, he missed the first free throw, he could yes or no make the second free throw. Similarly, whether or not he makes the second free throw, he could make or miss his third free throw. So I just draw all these branches in here to make a tree diagram, and they're not really looking as artistic as I would like. That's okay. Now, in a tree diagram, to help calculate probabilities, we label every branch of the tree with the probability of that event. Here, that's not that challenging to do because we know that Lillard has an 88% chance of making a free throw from the slides. So he has to have exactly a 100% minus 88% equals 12% chance of missing a free throw. Now I can label all these branches. I'm going to do that while this is paused just to save some time. Okay, you can see while I had paused the recording, I simply labeled all of these branches 80%, every branch where yes, he made, oh no, it was supposed to be 88% and 12%. Okay, I've corrected my mistake. Now every yes, a made free throw branch is labeled with 88%, the correct chance of making a free throw, and every no branch in my entire tree diagram is labeled with 12%, the correct chance of missing a free throw for Damian Lillard at the time I made that slide in the slideshow. Okay, now we want to find the probability of each outcome happening. Let's start at the beginning of the list, the probability of 0 shots being made. I'm going to color that blue, so like 0 shots being made. That would mean he'd have to miss his first free throw. Nope. Miss his second free throw. Nope. And miss his third free throw. Nope, nope, nope. If you recall how tree diagrams work, what's cool about them is to get the probability of all 3 no's happening, we just have to multiply 12% times 12% times 12%. You multiply the probabilities on the branches. That encodes what's called the general multiplication rule of probability in a picture, which is nice. So 12% times 12% times 12%. For short, I can write 12 to the third, 12% raised to the third power for the shorthand version, and then put it up here in my notes right there. The chance of not making any free throws out of 3 for Damian Lillard. Now, it's more complicated actually for making 1 shot or 2 shots because there's more than one path through the tree like that. So I'm going to, for my next probability calculation, I'm going to take a green path for making all 3 free throws. Yes, make the first free throw right there. yes, make the second free throw here, and yes, the third free throw. Okay. If you're paying attention at home, if we were in class, I'd ask you to put in the chat what's the probability of the 3 yeses. I would wait a second until one of y'all typed 88% times 88% times 88%, or if you prefer, 88% to the third power. That'll get that calculation correct. So I'll put that over in my table. Oh, notice I'm kind of working quickly. I'm not pausing to figure out those values. If you want to check these numbers as we're working together, just get them into your notes or something. That would be cool, and I'll double check them later with when we show how to work this with technology. I'll show you how that looks. Okay, let's look at either making 1 or making 2. How about the first one on the list is to make 1 free throw out of 3. Now, really, that would be my goal if I was going to take 3 free throws. If I made 1, I would be a happy Ralphie. Although my chance of success is not 88%, so let's not think about that. But let's look. 1 free throw made. You could make the first free throw like that. How do you love this rainbow tree? But if you made the first one, that's 1 make. You would then have to, or Lillard would have to miss the second and miss the third free throw, right? Or if Lillard missed his first free throw, going this path, he could then make his second free throw. That's making 1, and then he'd have to miss the third, right? Or after missing the first, he could also miss the second free throw and then make the third. So really there's 3 ways this could happen. He could miss 2 and make either his first or second or third free throw to make 1 free throw total. And we can see in the probability calculations, in every case, the probability of make the first free throw and miss the second and third is going to be, well, it's the 88% chance of making the first free throw multiplied by the 12% chance of missing the second and the 12% chance of missing the third. That's 2 factors of 12%, like that. Now, the order of multiplication is really not that important. So if you want the probability of missing the first free throw, making the second, and missing the third, well, there's still going to be 1 factor of 88% on that path and 2 factors of 12% on that path. Same exact calculation. And if we go down to the last way this could work, that's missing the first 2 free throws and making the third. Well, again, 1 factor of 88% multiplied by 2 factors of 12%, same calculation. Now, what we need is the total probability of making 1 free throw. So we have to add up the probability from each of those rows, right? So let me get over here into my notes on this side. The probability that Lillard makes exactly 1 out of 3 free throws, it's going to be, take that number and add it to itself, a couple of times. Oh, it's kind of messy. Let me, see that? Just like add up that same calculation, or for short, we could say 3 times that calculation. That's the probability that Lillard makes exactly 1 shot. The 3, that factor of 3 is how many paths through the tree. 3 paths through the tree, making the first, second, or third free throw. 1 factor of 88% for the single make, and then 2 factors of 12% for the 2 misses. Okay, that's kind of cool. So like, think of this little number. There's, see that? 1, 2, 3. That 3 right there. That 3 is like this 3. There's 3 paths, right? 3 paths through the tree. This little circled 3 right here that get you 1 make. Okay, kind of feels complicated at this point. If you're new to probability thinking and probability calculations, yeah. It's like when I'm at the mechanic's garage and he's working on my beautiful, or sorry, they're working on my beautiful dark gray Toyota Corolla, and they want to show me something about the engine, and I'm like, that looks complicated. Yeah, if you feel that way, it's fine, because this is pretty complicated. But I'm just going to talk through path for two makes. Our last option here, let's talk through this without as much typing. You got to make two shots. I do like making rainbows, so yes, make the first. Yes, make the second. That's two makes, and then to get a no, you got to get a miss right there. You can see this is just the remaining paths through the tree. You could make the first, miss the second, and make the third, or you could miss the first shot and make both the second and the third shots. So there's one, see that? There's one path here, two paths, three paths through the chart, and in each path, two makes and one miss for the three shots. So we can say that's three paths. Along each path, there are two factors of 88%, and you got to multiply them by the one factor of 12%, representing the, again, three paths through the tree is that factor. Two factors of 88% for the two made free throws, and one factor of 12% for the one missed free throw. Phew, okay. I was a math major, okay? One of the fun things about being a math major, if you're into it, is that you start to recognize numerical patterns. Let me look at this. What if I line stuff up to help my math major eyes recognize a pattern? See what I'm doing here? I'm just lining up the 12% factors in those multiplications. I'm lining up these factors of 88%. And as a math kid, grown up, sorry, I'm a math grown up. I got 2 math degrees. That's a lot. And I dropped out of a program for a 3rd math degree. But I know some stuff as a math major, some nerdy stuff, like one factor of 88% right there. That's the same as exponent 1. I can write raised to the exponent 1, just one factor of 88%. And that makes that pattern 3 here, 2 here, 1 here. Kind of cool. And over here in the 12% zone, same thing. 3 factors of 12% for 0 makes, 2 factors of 12% for 1 make. It's really 1 factor of 12% for 2 makes. And hey, I'm a math major. I can remember that if you don't multiply by something, it's 0 factors or a 0 exponent, just like that. And look at that pattern, 12% raised to the 3rd, 2nd, 1st, 0th pattern. Hey, I could do the same thing over here with the 88%. Isn't that cool? That pattern, 1 make is, isn't that pattern cool? You have 0 makes, you have 0 factors of 88%, 1 make, 1 factor of 88%, 2 makes, 2 factors, 3 makes, 3 factors, okay? And also, math folks, like me, I'm a math nerd. Look at that. I see 3 is the number of paths through the tree for 2 makes and for 1 make. And I can see there's only 1 path through the tree for 0 makes. And I can see in the last row here, there's 1 path through the tree for 3 makes. Isn't that cool? So this first number is the number of paths through the tree for each corresponding number of made baskets. Second factor is the probability of success of a made free throw raised to the number of free throws that Lillard took, 0, 1, 2, and 3 for 0, 1, 2, and 3 makes. Okay, and then the exponents on the chance of failure, 12%. Well, if he has no successes, he has the number of tries 3 factors of the failure, 12%, that drops down in this pattern. Isn't this pattern so cool? Look at this pattern. Are you feeling like a math major? Do you love that pattern? You might want to be a math major if you love the pattern. Okay, now I got to calculate all these numbers, and that's going to take some typing into a computer for me. I could go type up all those numbers in my calculator, or I could use my little buddy, Geogebra. Notice that all I needed to know, number-wise, to do all these calculations for this binomial distribution, all I needed to know was that the number of trials, the number of free throws is 3, and that the probability of success is 88%. With just that knowledge, I could draw the whole tree, list out all the outcomes, and figure out everything I just did, knowing 3 tries, chance of a so-called success, 88%. Now, what's cool is Geogebra will calculate all these probabilities for us very quickly and very accurately, knowing only those 2 numbers. Let me show you how that works over there in our buddy, the computer. I'm going to geogebra.org/classic #probability. That's our probability calculator in Geogebra. We had a Zoom session. I'd copy and paste the address, there it is, into the chat. But geogebra.org/classic, and then in the main menu, you can select probability calculator. When we're here, we haven't messed with it yet, but you'll land on the distribution side, which is where you want to be, and you'll notice that this normal distribution we're looking at, the bell curve that we studied in the previous couple of sections, that's a menu. So in that menu, pop that open, and you'll see just below that dashed line, your option is binomial. So in here, in the probability calculator, distribution side, in the menu, select binomial, and you land right here at geogebra.org/classics, binomial distribution calculator. Really cool. It has 2 parameters you can enter. N, that's your number, where we're talking about 3 free throws taken. Type that right there. And little lowercase p, the probability of success for Lillard, that's an 88% chance of making a free throw. And the second I've typed in both those values, look up here in the corner where I'm bringing your eyeballs right there. Bang, there are the 0, 1, 2, and 3 K, the outcomes, the possible numbers of success, and right there are the probabilities of success. Isn't that so cool? Just those are the numbers that if you've been checking my calculations in your notes, like I kind of asked, those are the results that we needed to finish our probability model work back in our class notes. So it's 0017 is this one. Oops. Like that. The next one, the probability of 1 free throw going in is 038, and a 0 would be the last digit. Round it off. The probability of making 2 free throws is 2788 after that decimal, so 2,788 10,000ths, 2788. And the chance of making all 3 free throws is also the most likely result for Damian Lillard, as you can see both in the graph and on our list, 6815 after a decimal. And wow, now we also here have the same probability distribution that GeoGebra gave us in like 1 second. All the outcomes with their corresponding probabilities in a list. Although our version has all the calculations because we took the time to look at every detail of the probability calculations. You don't need to do all those details. in your work. If you're working on binomial distribution homework problems in I think the 4th section of the 4th chapter of our text, or a problem on our final exam for which this technique works, I want you to go directly to geogebra.org/classic #probability. Set this thing up to use the binomial distribution and get this calculation done quickly and accurately. Okay? Okay. Now let's head back to our slides. Yeah, we made it to bullet 3. There it is. Binomial 3, short for n equals 3, the number of tries, and 88%, short for little p equals 88%, the probability of a so-called success. That's an example of a binomial distribution. It describes how many yeses you get out of a set number of tries with a set probability. Kind of cool. So a binomial distribution describes the likelihood of the number of so-called successes, k, out of a specified number, n, of independent success-failure trials. If lowercase p represents the probability of success, then 1 minus p represents the probability of failure. N represents the number of independent trials, probability is always the same, and k represents the number of successes. There's a formula that captures what we did over on the slides. You'll notice it's got some ingredients. The probability of k successes out of n tries is 3 numbers multiplied together. This n over k in parentheses is read n choose k by mathematicians. It's called a combination number, and that's the number that tells you how many paths through the tree would get you that many successes. P raised to the kth power is the next factor. That's like our 88% to the second power. For 2 makes, we'd get 2 factors of 88%. And then this 1 minus p raised to the power n minus k, that's our third factor. It's like 12% raised to the first power would mean you need 1 failure to go with 2 successes back in our example. Again, you'll see noted on the slide right here, we don't need to use this complicated formula in daily life. I personally never ever use it. Like, I haven't typed except to show the engine of this thing, like in our example just now. I never use this for calculations. Heck, even in our example, once I typed up all the calculations that actually do use the formula, I still just went to GeoGebra to get the results because it's faster than typing in all those numbers. So remember, GeoGebra probability calculator, binomial distribution is your pal for these kinds of calculations. And it's a good pal because the by hand calculations get pretty complicated and convoluted when the number of attempts gets bigger. Our second example, we're asking to let k be the number of free throws Damian Lillard makes out of not 3, but 20 attempts, a much bigger number. And then there are 4 probability questions here. Or sorry, 3 probability questions and one about the mean and standard deviation of random variable k and some consideration of their meanings. Let's work these through one at a time. But first, let me just pause the video. I just want to get a drink of water and catch my breath. So be right back. Hey, thanks for letting me go get a little drink. I grabbed myself a Polar 100% natural seltzer, calorie-free, original bubbly water drink. This is not an advertisement for this seltzer drink. It's just an admission that I really like it. It's refreshing and it doesn't keep me up late. Okay, and on the break I also typed up symbolically these 4 ideas. What is the probability Lillard makes 13 free throws? That's capital P for probability. K, Lillard makes out of 20 equals 13 free throws. So it's shorthand for these 3 things. Probability that he makes at most 15 free throws. Oh, there's a typo right there. That's up to and including 15 free throws. So I used less than or equal for that one. Third one, probability that Lillard makes over more than 17 free throws, so a greater than symbol. And then just a note, mean and standard deviation, and we'll remember to explain their meanings when we get there. Let's head over to Geogebra to work on this. Remember, we're doing n is 20 now instead of 3, still the same 88% probability of so-called success, a made free throw in this case. Hey Geogebra, here we come. Okay. N is 20 goes right here in the number n field. So I switch that to 20. I'm leaving the 88% all alone. And you can see now the graph has more space all the way from 0 up to 20 on the axis describing the number of possible successes. We can see the same thing, 0, 1, 2, 3, all the way down if we scroll to 20 possible successes and their individual probabilities over here on this list. Hey, wait a minute. Our first question was, what's the probability he makes 13 free throws? I can see it on the list over there. 0053 is right there on the list. About a half, or about, a 0.5% chance of making exactly 13 free throws out of 20. Very rare event. You can see it's a very small bar in the histogram that shows all these probabilities. Okay, you can also calculate that directly using the interval setting down here. Let me get my pointer back. Hey pointer. Here in the interval setting, we can just type into those two fields 2 13s, a 13 there, a 13 there. Now that'll light up in the drawing that 13 only and also 13 only in its row in the table, 0053 right there in the output at the bottom of this little calculator. Pretty cool. Okay, the probability that k is less than or equal to 15, well, less than or equal to, that's our left-sided calculation device down here. So I'll select left-sided. And now I want to go up to and including 15, just like it says in my notes. P, they use an X instead of a K in GeoGebra. That's cool. Just a different letter choice. I just type a 15. I can see in the graph all the bars up to and including 15 are colored in bright blue. All those numbers of outcomes 0 through 15 lit up in the table on the right. And the computer adds up all those tiny probabilities I can see on the table to 0827. Or about 8.3% chance, right, of making no more than 15 free throws as described on the slide. Okay, third option, probability k greater than 17. All right, I don't want to go to the left, I want to go to the right, so I'm going to come down here and grab my little right-sided option for the calculator. Right-sided, click, that flips the thing around, and I want to go greater than 17, right? Greater than 17. Now, just eyeballs wise, let me use a bright color here. Greater than 17 is not the same thing as that symbol's an or equal to, right? So to be greater than 17, I've got to be greater than or equal to 18. So just a little adjustment there to make the way the question's phrased. I got to be careful. That's the same as the equal to the probability that the number is greater than or equal to 18. That's how the calculator does it. So now I grab the right tool. I type my 18 right here. I can see right there it lights up the 18, 19, and 20 bars in the histogram. On the list, all of the amounts that are greater than or more than 17 are lit up. They're added up for a 5, 6, 3, 1 after a decimal probability. Yeah, 56.3% chance of making more than 17 free throws. Mean and standard deviation question mark? Well, it's a histogram, so the mean has to be at the balance point. Our old buddy for the mean, oh, yellow might not be the best eyeballs wise. Let's go blue. The mean is the balance point. Let's go estimate it graphically. If I just come up here and say, okay, it's skewed off to the left a little bit, something like that. Would you believe me if I said the mean was like right about 7, something like that? Like, yeah, something like that. You buy that? Mean value, balance point. Also, remember the symbol for the mean of a random variable is mu, the Greek letter mu. And notice right up there, there's your Greek letter mu, and there's 17.6, the balance point of this distribution. And that's just right. So mean mu is 17.6. That's 88% of 20. So like over the long term, if Lillard took like groups of 20 free throws again and again, and sometimes he made 19, sometimes he made 15, sometimes he made all 20, sometimes he made 16 or 18 or whatever numbers, and some assistant coach, like every practice he took 20 free throws, and an assistant coach like wrote down how many he made. Over the long term, if the likelihood of success stayed the same, yeah, he'd make 17.6 shots on average. So it's like the long-term average. If you could repeat the experiment again and again, and then, well, the standard deviation sigma, standard deviation is that letter sigma. It's right up there as well in our output. Sigma is 1.4533. And if I draw a couple little arrows about that long, so that's 1 and almost a half, and then 1 and almost a half. So artistic. Look at me just drawing things here. It's not even like early. It's like 10 o'clock at night while I'm working. So, I'm working at night here. It's because I'm disorganized. You can see it got dark. See, check it out. It's dark outside. Whoa, it's dark. The darkness out the window right there. Whoa. But you can see those little arrows get us approximately the standard deviation, and that's like, the expected deviation from the mean over the long term for those outcomes, according to these probabilities. Kind of harder to write a little sentence saying that, but just knowing it's the standard deviation of the outcome is enough to know. Okay, cool. That's how the calculator works. So be sure to use that, to use this tool when you're asked to do these kinds of calculations on your homework or on your final exam. You hear binomial distribution, end up right here. Binomial distribution at Geogebra Classic, and you're in the right place to get these done quickly and accurately. Hooray! Okay, another example. If the probability of developing a severe lung condition for a smoker is 3/10 or 30%, what is the distribution of the number of cases of severe lung conditions among 4 randomly chosen people who smoke? Okay, find the probabilities for 0, 1, 2, 3, and 4 using technology. No problem. We just talked about how great GeoGebra is for this. Our N is 4. Let me write my notes down. N is 4, and P is 30%. I head back to GeoGebra. N is 4 now. P, the probability of, see why success is not a good choice, kind of a tone-deaf choice by statisticians. No one's going to call developing a severe lung condition a success. It's yes to the question, did someone or will someone develop a severe lung condition? But there's the picture, and we can see right here on this side of our zone, there's all four probabilities they asked about. Sorry, all five probabilities they asked about on the slide, just immediately calculated and put in a table for us so nicely by technology. Yay, technology! And on the slides, you can see the distribution is below as written out by the textbook and slides writer. They spent the time typing up how to use the formula for all these things to type into a calculator. Though, I would never recommend you do that. Heck, I've never even showed you how to calculate these combination numbers in a calculator. If you are curious about those combination numbers and want to know how they work kind of by hand, I will break down that formula for you. Just ask either during class or during any other time you can access me to talk math. It is kind of an interesting calculation, but again, you don't have to know it to be able to get these calculations done quickly and accurately. The next slide shows the same probabilities we see in GeoGebra and the same graph, right? Isn't that cool? That GeoGebra gives us the same lovely graph of how this could go. We can immediately see the most common outcome is one smoker of 4, with that chance of developing a severe lung condition would do so. And we can see that they're spread out. 0 and 2 are also rather likely, while 3 or all 4 smokers developing a severe lung condition are less likely graphically. Mean mu is 1.2. That's 30% of 4. And the standard deviation here is nearly 1, about a little more than 9/10 standard deviation. Kind of cool. A couple of slides here that describe how to calculate that standard deviation and that mean. They note here on this slide that we had formulas. When we have a discrete random variable with numerical outcomes and their corresponding probabilities, we could use some pretty complicated formulas to figure out their expected value, E of x, or the mean, mu of x, the way they draw it on this slide, or to figure out the standard deviation of x, also known as sigma, as the square root of the variance of the random variable x, which is a pretty complicated calculation itself. We even used GeoGebra for these calculations back when we studied this, a week or two ago? Fortunately, for the binomial distribution with the parameters n, number of random events, and p, set probability of success, there's much less complicated formulas for both of these. This was nice back in the olden days before computers. Nowadays, GeoGebra gives us these numbers immediately, as we've already seen. I've already talked about how the mean or expected value is calculated by just the percentage of the number of attempts. Here's an example illustrating that. A 2012 Gallup survey suggests that 26.2% of Americans meet a definition of obesity. Let's pause just to remind ourselves that being big, being fat, doesn't necessarily mean someone's unhealthy. Just like being thin doesn't necessarily mean someone is healthy. Every person's body, no matter weight or size or shape, is a beautiful thing, and we should fight fat phobia in ourselves and in our culture. It's really cruel and it's deadly for a lot of young girls and young people, actually, not just girls. So yeah, let's fight fat phobia. I'll just refer to this as the definition of obesity. I'm just gonna, it's on the slides. I'm not going to try to edit it out. It's a rough thing to think about, that pressure on people. Okay, back to the example. So if 26.2% of people in this country meet that definition, among a sample of 100 random people, how many would we expect to meet the definition? That's not hard. We just say, okay, 26.2, that's 26.2% of 100 is 26.2, or just round it off to about 26 people would be expected to meet that definition out of a random group of 100. Not hard. And that's the formula for the mean, mu, of a binomial distribution is just take the number of attempts, multiply it by the probability of so-called success, and you've got the expected value, or the mean. Of course, this doesn't mean that every random sample of 100 people would have 26 and 2/10. Well, you never get 2/10 people, so that's silly. But yeah, you'd see the value be higher or lower. That would simply be the average among lots of different samples of how many people meet that definition. You can see here on this slide, the calculation for the mean is quite simple. Just number of attempts times probability of so-called success. The calculation for the standard deviation's slightly more complicated. Multiply the number of attempts by the probability of yes to the question. Multiply that by the probability of no to the question, 1 minus p, and then take the square root of that product. That gets us the standard deviation that GeoGebra calculates for us quickly and accurately. For the so-called obesity rate, just plugging in the values from the previous slide, we can see the standard deviation would be 4.4. Now, using GeoGebra is how I actually do these calculations. If we had 100 people, chance of meeting that definition was 26 and 2/10%. And you can see up here at the top of this slide, we've got 26.2 mean and 4.4 if you round to the tenths for standard deviation. GeoGebra just gives 4 decimal accuracy is the preset. So the formulas are in the textbook. You can use those, or simply use GeoGebra to quickly and accurately calculate mean and standard deviation for a binomial distribution. Okay. So, and then there's their description of how that works out back in context at the bottom of this slide. Excuse me, I ate a delicious burrito before making this video, and it's giving me a little, stuff. Okay, unusual observations. Using the notion that observations that are more than 2 standard deviations away from their mean as being considered unusual, statisticians can calculate a range for the plausible number of people who would meet that obesity definition among random samples of 100 people. All they're doing down here, you can see, is taking the mean, adding and subtracting 2 times that standard deviation to get a range. From 17 and 4/10 to 35 would be about the, how did they put this on their notes? Yeah. That's like the range between, in a sample of 100 people, you'd expect between 17 and 35 people to meet that definition of obesity. Wow, that's not quite a quarter and up to a third. So again, a reminder, meeting an obesity definition does not mean someone's unhealthy or unattractive. It just means that they meet a definition. That's it, arbitrary one. Okay, next problem, and I think this one, if I remember, this one might be, is this the, one of these examples is our participation quiz. I'm leaving the participation quiz for you to investigate on your own after watching this video, or wait until we come back together in real life, or sorry, in a Zoom session when we're together, and we'll discuss it kind of as review for these video discussions where it's just me, lonely me. But back in August 2012, Gallup did a poll suggesting 13% of people in the US think homeschooling provides an excellent education for children. They're focusing in this large graph on that specific excellent percentage is 13 for homeschooling. Just that 1% out of this entire graph, or sorry, this entire table is what we're looking at. Would a random sample of 1,000 Americans where only 100 share this opinion be considered unusual. And let's just see how the slide feels about it, because it's getting late for me. It's almost bedtime. They are taking the mean of this binomial distribution. That's 1,000 times 13%, or 130 is what you'd expect in general. They calculate the standard deviation. We could do that using GeoGebra if we like, but they did it by hand by typing out the calculation. 1,000 people times 13% chance of a yes. That person believes homeschooling is an excellent education. Multiply that by the 87% chance that someone would say, no, probably not excellent, maybe very good or medium or poor, or whatever the other categories were for rating that. But that number is 10.6 to the nearest 10th. Then what they do is consider that range of usual observations. 130 is the mean. See that? So mean 130. Add and subtract double this standard deviation, sigma 10.6. The range goes down to 108.8. That is 100 is less than 108.8. It's outside the range of usual observations. That makes it unusual. That's method one. Method two, they used our old buddy z-scores, or standardized scores. Once you've got the mean and standard deviation, you can find the z-score of that observation, subtracting 100, that's the one we had in the question, subtract away the mean 130, divide by standard deviation 10.6, we've got negative 2.83, which says that a sample of 1,000 people with only 100 sharing this view is 2 and 8,300 standard deviations below the mean, below expectation. So that's pretty unusual as well. Yeah. Pretty unusual. Want to see method three? There's method three. We could use GeoGebra too. Check it out. 1,000 people, chance of success is 13%. 1,000 is my N. 13% is my P. Oh, my computer's getting a little bit tired. Okay, and then just, I could go less than or equal to 100. By just getting down to 100 or even fewer, that's only a less than like 1% chance of being at 100 or less. So any value under 100 people, or 100 or fewer, would be really, really unlikely. And even adding them all up, it's still less than a 1% chance. So definitely unusual. 3 methods. Yeah. Now, this next section is about what's called the normal distribution for the binomial, the normal approximation for the binomial distribution. And the first idea they share with us is on this slide, which you'll notice is dark gray, right? This is an optional topic. I'm not going to ever have this show up on your exam or anywhere else where I'm scoring your work directly. So, but it will show up in your homework. Now, there's hollow histograms here for setting a binomial model up with probability of success 10. Let me do it over here. Probability of success 10. Oh, buddy. Oh, internet. Are you okay? You're so slow. And starting at sample size 10 is their first graph there. And I could make that in GeoGebra just as well. Sample size 10 looks like that. Same graph as we saw on the slide. And you can see when the sample size is only 10 and the likelihood of a yes, or a so-called success, is only 10%, this is a skewed right distribution. The skewed right way off to the right, because there's just no room for any tail below 0 so-called successes. There you go. Heck, I could even, instead of drawing that normal curve with my tool, I can turn one on, I think, in GeoGebra, that little red normal curve. we'll draw a normal curve over the distribution with the mean and standard deviation of the distribution. And notice, yeah, the tail on the left gets cut off because we just run out of room at 0. So we have a skewed right distribution. Now, when we go up the number of attempts from 10 to 30, let's look back here in GeoGebra from 10 to 30. Okay, there's not as much skew here. I still like drawing it better than turning on the thing here. But we can see that if I draw through the peaks, like right there, it would be pretty symmetric, but then there's just more off to the right. Still skewed to the right because there's more space for the tail off to the right. Okay, what's our next sample size to bump up to? They say on the slide. Let's bump it up to about 100 for sample size n. When I do that, go to sample size 100. Now, looky there. When I draw my smooth curve over that binomial distribution, there is room on both sides for that tail to come right down there near that horizontal axis. And that looks kind of nice. And notice a little bonus. If you notice over here, where's my pointer? Looky there at 0 successes, 0 yeses to whatever the question were, the probability of success rounds away to 0. The probability of that happening is so minuscule it rounds off to 0 at 4 decimal places. That's kind of visually when you get enough space for that curve to happen. And for even larger sample sizes, for still larger sample sizes like 300, no problem. Now there's plenty of space if we go to 300 here. I don't even think I need to draw a smooth curve over those bars to show that they really look like a unimodal symmetric bell-shaped normal curve. And if I turn on the red one, it really closely follows those blue bars up and down very, very closely. Kind of cool. And you'll notice now there's plenty of room, all sorts of zeros down here at the low end, 0 all the way up to 11. Those are all so small that there's just plenty of room for that tail right there. Okay, now back in the olden days, statisticians liked this because it allowed them to use the normal model when it was like going to fit on the graph that way to do approximations for binomial probability calculations. The reason they liked that is they didn't have calculators or computers that could do the binomial calculations as quickly and accurately as they'd liked. So it's due to technical limitations that people started using a normal approximation for binomial distribution calculations. And that worked out as long as you expected both 10 or more so-called successes, so n times p being 10 or greater, and 10 or more so-called failures, that's n times the chance of failure, 1 minus p, being 10 or greater. Yeah, and so they give a couple examples of how those numbers work out for the graphs that we looked at on the previous slide. In modern times, we don't really care about this, so we're going to skip this slide a lot, skipping it, yeah. And we can even talk about an example here that they give to use this normal approximation. We'll just use the GeoGebra to solve it. It's kind of a cool example. It's about Facebook users. A recent study found that Facebook users get more than they give. For example, 40% of Facebook users in their sample made a friend request, but 63% received at least one request. That makes sense because I almost never have ever requested anybody be my friend on any social media at all. It just feels weird. I don't know why. Users in our sample pressed the like button next to friends content an average of 14 times. I do like people's content. But had their own content liked an average of 20 times. Users sent 9 personal messages but received 12. This is all on average. 12% of users tagged a friend in a photo, but 35% were themselves tagged in a photo. Any guesses for how this pattern can be explained? Well, there's no time to talk about this because there's no one else here but me. The reason is that some people on Facebook, or really any social media site, are very active and they do a lot of stuff and they drive up the averages. Power users are what they're called, and they contribute a lot more content into a social media site than typical users. That's how that works. This study also found that approximately 25% of Facebook users, this is back in like 2012, were considered power users. The same study found that the average Facebook user has 245 friends. What is the probability that the average Facebook user with 245 friends has 70 or more friends who would be considered power users? Okay, let's just answer this with using our buddy, the binomial distribution, because we can parse this out. 245 friends would mean that there's 245 chances for someone to be a power user here. And the probability that any of them happens to be a power user is 25%. The assumption we'd have to make is really that no one's power user status affects anyone else's. That is, even if one of my friends was doing a lot of stuff on Facebook, it wouldn't influence me to do more stuff, I guess. Realistic assumption, maybe, maybe not. But then their question here is, what's the probability that someone has 70 or more power users among their friends with these counts and likelihoods? Okay, let's just cruise over to Geogebra to answer this question kind of quickly and accurately. N is 245. Probability of so-called success is 25%. We're going to look for greater than or equal to 70, so I'm going to go to the right-sided selector there and 70 here. That'll get me my answer. A little more than an 11% chance of this happening. There's an 11.3% chance of having 70 or more power users among 245 random, Facebook users back in the day. It's changed a lot, right? Facebook is much, much different in 2022 than it was in 2012 when this problem was written. There's a lot more competition in the social media space. TikTok, Twitter, Discord, Twitchy, YouTubes, different stuff you can do online than there were back then. Facebook really took off and sort of set the mold. Okay, back on the slide, they do a different thing. So we did that. We went technology. So our technology calculation got us the number we got that's now kind of hidden up in that mess. But we might need to look at it again in a minute. So I'm not going to delete that big mess yet. Back in the days before computers, though, this was done using the normal approximation for the binomial distribution. Actually, I will clear this off. And the way that worked was they'd find the mean and standard deviation of the binomial distribution using those formulas. So 245 times 25% is the 61.25 mean of the binomial distribution. Sigma standard deviation to 245 times 25% times 75%, the remainder. Take the square root of that product for 6.78 standard deviation. And then they'd use the normal distribution with that mean and standard deviation. You can see it drawn here in blue on the graph, and calculate the probability using normal distribution methods. Because back in the olden days, they had a nice table of values in the back of a book or in a book on a shelf of statistical value tables to do this calculation quickly. You'll notice that when they did it in this old-fashioned way, the probability is a little lower. It's only 9. It's a little bit less than 10%. That's just normal. It differs because there's some funkiness in the modeling. We're not too concerned about that, so don't worry about it. And I think this gets us to the end of the slideshow. We made it. Oh my goodness. Yay. I gotta get to bed pretty soon, so I gotta just say goodnight. I hope this was helpful for folks learning more about the binomial distribution. Work on the homework from this section, and when you have questions, bring them to class when we get back together in Zoom sessions if you're a Zoom session attendee, or bring them to me via email or in one-on-one support times. I hope this was helpful. It was weird doing it by myself, so have a good one.